Welcome to another episode of NASA Science Live, an opportunity for you to interact with NASA experts and have your questions answered in real time. I'm your host, Megan Cruz, and today we will talk about some of the extreme weather conditions we've been seeing across North America. In fact, just hours ago, NASA announced that July 2023 was the hottest month ever recorded on Earth. It was also the hottest July on record, according to NASA's global temperature analysis. If you have questions throughout today's show, you can send them in using the hashtag AskNASA on social media or drop them into the comments section wherever you're watching us today. Now, joining me now are two climate experts to discuss this record breaking news and explain what we can do moving forward. Dr. Kate Calvin, NASA's Chief Scientist and Senior Climate Advisor, and Dr. Gavin Schmidt, Director of NASA's Goddard Institute for Space Studies. Thank you both for being here.
Thank you for having us.
Thank you.
So again, today NASA announced that July 2023 was the hottest month ever recorded on Earth. We know this and can say this with confidence because of NASA's global temperature record. Gavin, can you explain what this record is and what this July looks like in the context of that bigger picture?
Absolutely. NASA gathers information from weather stations around the globe, from ocean buoys, from ship records, from automatic weather stations, and it kind of knits it together to produce an estimate of the global mean changes over time. And we can do that accurately going back to roughly the mid-19th century. And what we've seen in recent years is ongoing global warming. But what we've seen specifically this month is that this July was so much warmer than all previous Julys. And because July itself is in fact one of the warmest months of the year globally, that means that it was the absolutely warmest month in that whole record, going back at least to the mid-19th century. One of the things that we also do is we can compare that to other estimates of what's going on through what are called reanalyses, which is the weather forecast models, or directly from satellite instruments. And all of those sources of information confirm that July was record anomalously warm across vast swaths of the globe.
Yeah, and that graphic we really saw this July spike in comparison to all the other average changes we've seen in the record. How much more is this July that change than other changes we've seen prior?
So the margin by which the record was broken was over zero point 0.2 Celsius, which is almost half a degree Fahrenheit, and the uncertainty in one of those numbers is just like 0.08. So the difference between 2023 and 2019, which was the previous record, was hugely significant.
Yeah, big difference there. So we know we have the hottest month on record. Kate, how is the rising global average temperature and the climate change manifesting in these different kinds of weather, extreme weather we've been seeing across North America?
Yeah, thanks, Megan. So climate change is more than just changes in temperature. There's other changes that we see in the Earth system, things like increases in sea level, declines in Arctic sea ice. We see changes in the water cycle, so you get more heavy precipitation events, heavy rainfalls, and in some regions more droughts. We also see more extreme events like heat waves or wildfire. For something like a wildfire, climate change can affect both the fuel for fire, so it can dry out vegetation so that there's more that can burn. It can also produce fire weather, so conditions where it's hot, dry, and windy, and they're very conducive to fire. And climate change drives all of those. And at NASA, part of what we do is observe what's happening in different parts of the Earth system, both now and as it changes over time, so that we can study those effects and how they're changing. So for something like sea level, we have one satellite or a series of satellites that have been able to show us total sea level, so we can see how much sea level has risen all around the world. But we have other satellites that'll show us some of the contributing factors to that. So we have another set of satellites that have been able to show us changes in the mass of ice sheets. So as ice sheets melt, that water runs off into the ocean and contributes to sea level rise. And we're able to see those effects of climate change and how they're changing over time.
So we have a lot of opportunities to track the effects, but then what are the causes and how has NASA identified those causes?
Right. So NASA is keeping track of the causes of climate change too, whether that's changes in greenhouse gas concentrations, changes in the activity of the sun, changes in the stratosphere because of volcanic effects, changes in the natural system, whether there's an El Nino or a La Nina. NASA is looking at all of those different elements as well. Atmospheric pollution, deforestation, all of that comes from NASA data, and then we can integrate that information using climate models, using statistical models to try and piece together what the fingerprints are of any of those different changes, and then fit those fingerprints to the evidence that we have. And when we do that, what we find is that the long-term trends that we're seeing, that you saw in that earlier graph, are all due to human activity. Dominant in that is the role of greenhouse gases, carbon dioxide, methane, CFCs, and there's little roles for all of those other things as well. But the main result from that analysis is that those trends that we're seeing, that are pushing us ever warmer, are really just a function of our increases in greenhouse gas emissions.
So in being able to pinpoint, this major contributor, why we're seeing what we're seeing, what is NASA doing to help communities tackle climate change when you do know the majority cause?
Yeah, thank you. So one of the things that we do at NASA is that we're observing the Earth. So we're seeing these changes, we're seeing what the Earth looks like now, as well as how it's changed over time. And we provide all that information publicly so that people can use that in their decision making and in their understanding of what's happening in their communities. So just like a few examples of things that we've provided. One, when we're talking about greenhouse gases, we have an instrument on the International Space Station called EMIT. EMIT was designed to study mineral dust, which can reflect or absorb sunlight, but it also can identify methane superemitters. And so we're putting that information out publicly so people know where those methane plumes are coming from and can use that. We also have another tool called OpenET that's helping farmers better plan their irrigation. So it can tell how much water is coming off of their crops out of the soils and better plan when to put irrigation back in, and so that their crops will produce better crops going forward. And so we do all that information and make that all publicly available. We're also developing technologies that can help people respond to climate change. So everything from sustainable aviation to we do research in growing crops. Some of that's done on the International Space Station, but has benefits right here on Earth.
Yeah, I think it's great that we make that data publicly available so that people can change their actions if there's something that they can do to help curb what we're seeing. So we have a lot of questions already coming in from viewers watching online. Remember, you can submit questions using hashtag AskNASA or posting them in the comments wherever you're watching us today. So if you're ready, guys, the first question is from Emil on Instagram and asks, will these records keep being broken, or is there a maximum of heat possible in global temperature?
Yeah. So the bad news is that these records will continue to be broken. We will expect record-breaking August temperatures as well, given the ongoing incipient El Nino event in the tropical Pacific. We expect that records for the rest of 2023 will start to break records too. 2023 might not quite be the warmest year on record, but it'll be very close. And 2024 will very likely be the warmest year on record. That's in the short term. In the longer term, we're going to continue breaking these records as long as we continue to emit greenhouse gases. Perhaps not every year because of the the ups and downs of natural variability. But what we will see is that every few years we will be getting new record temperatures being set. Now, is there an absolute maximum? That's a little bit hard to say. I think if you look at the other planets in the solar system, particularly Venus, it might be that maximum temperature is extremely uncomfortable for humanity and indeed all life. So unfortunately, there's no global thermostat that is going to suddenly come and make this all go away. Sorry.
Yeah, and just to add to that, so there is a science community that looks a lot at projecting climate change into the future, and Gavin and I have both done a lot of work in that. And really, what you find from all of that work is that future warming depends on future emissions, and so they can look at how much warmer it'll get in the future. But there's a lot of options there because it depends on how much we emit between now and that point in the future.
Thank you both for those answers. The next question comes from at the side of the sun on X and asks, why not just release actual temperatures rather than temp anomaly on the y-axis?
That's a great question. So what is it that we're doing here? We're putting together an estimate of the global mean. Now, there's no one measurement that is the global mean temperature. You can't get that from space. You can't get that from a single station. And so when you want to look at what's happening at the globe altogether, you have to put together a lot of different raw data. So you can go and download the raw data that goes into these calculations. In fact, you can download all the code and you can just do the calculation yourself. And feel free to scoop us next month. But we're using the raw data and then we're just kind of stitching it together statistically to get a best estimate of what the global mean change is. And it's important to know what the uncertainties are in these things. So for the annual mean, it's around 5/100ths of a degree for the annual. For a monthly mean like this, it's about 8/100ths of a degree uncertainty because of that stitching process. And you can check whether different methods give you a different answer, and unfortunately they don't. So whether you look at the weather models, whether you look at the satellite data or the atmospheric temperature data or other people's methodologies, all of those things are lined up and are saying that July 2023 was record-breakingly warm.
John Weigel on Instagram asks, how are scientists able to estimate climates thousands of years ago?
Well, I might as well take that as well. So the instrumental record, as you can see in that graph, went back to roughly the mid-19th century. Our information about climates beyond that rely on what are called proxy records. So these are things like ice cores or tree rings or cave records or ocean sediments where there's some geophysical or biological factor that responds to the climate. For instance, we can see where the ice sheets used to be 20,000 years ago because they've left literal scars in the landscape that we can date, that we can assess. And so there's been a community of folks working on that kind of question for about the last 50 years. And so our estimates of what happened during the Holocene, what happened during the last ice ages, when it was last as warm as we think it might be back in the Pliocene or the Miocene or in the Cretaceous. All of those things are built from big networks of proxy data that have been put together relatively well, and we don't have the accuracy for those past data that we have for July during the modern period, but it does give you a sense of where we are with respect to that kind of context of change.
Mm-hmm. Kate, why don't you take this next one from Brianna Rodriguez on Instagram? She wrote, what are the 3 biggest causes of climate change? We talked about the first one, but she's interested to see other causes.
Yeah, so if you think about how warm it is on a planet, any planet, whether it's Earth or not, you've got an amount of sunlight that's coming in, and that has to do with how close you are to your star, the angle of the surface. Then you have some of that that's reflected back into space based on the color of the surface, and some of that that's absorbed or trapped. So greenhouse gases will trap heat. So on Earth, greenhouse gases, and namely carbon dioxide, methane, and some other gases are trapping heat. So when we have sunlight coming in, we're trapping a lot of that. There is some that's reflected back into space, and the color of the Earth's surface affects that. So darker colors absorb more heat, lighter colors reflect it. We also have things like the oceans will absorb some of the carbon. So when we burn fossil fuels on the Earth's surface, some of that goes into the atmosphere and is trapping heat. Some of it is absorbed by land and by ocean. If you look at numbers, so human activities are what's causing climate change on Earth now. So we can attribute the climate change we're experiencing. Greenhouse gases in particular actually lead to more warming than the total warming we experience, because other aspects of human activities like sulfur will reflect that and lead to a cooling effect. So I'd say if you're looking for the simple, human activities, principally greenhouse gases, are warming the planet, is probably the most straightforward way to say that.
I think maybe if I just add very briefly. So in terms of the individual gases, the dominant thing is carbon dioxide, followed by methane, followed by chlorofluorocarbons, CFCs, and then ozone. And that's slightly balanced by sulfate emissions, nitrate emissions, and deforestation. But the two biggest things are carbon dioxide and methane.
A few viewers are wondering about today's temperature announcement and if there are connections between this and the Tonga volcano eruption in the South Pacific last year. Could you explain?
Sure. So one of the things that NASA does is that we look at all sorts of aspects of the Earth system, and one of the instruments on a satellite called Aura is the microwave limb sounder, and that is able to give us pictures of how much water vapor there is in the atmosphere, going all the way up from the tropopause to the mesopause. So very high up in the atmosphere indeed. And what that's shown is that the Hunga Tonga eruption added about 10% of the total stratospheric water vapor up to levels of 30, 50 kilometers above. And so we've been very interested in that. That's a unique thing that we have seen over the satellite era. And we've been looking to see what impact that has. It has a very clear impact in the stratosphere because the stratosphere is so dry. Water vapor is a greenhouse gas, so we expect it to nudge us a little bit towards warming. But the numbers, when we've done the calculations, are not very large. They are around 0.03 of a degree warming Celsius. And so that is enough to give us a little nudge, but it isn't enough to explain what's happening independent of all the other things that are going on.
Gotcha. So July 2023 was 0.43 degrees Fahrenheit warmer than any other July in NASA's record. Laurel Darrow on Facebook asks, is that even statistically significant?
Great question, and the answer is yes. So the anomaly, the uncertainty in any 1 month's anomaly is around 0.08 degrees Celsius, and this was about more than 0.2. So it's 2 or 3 times larger than the 95% confidence interval. So there's no question that this is a significant warming and that it is real.
Right. El May on YouTube asks, has El Nino affected temperatures this summer?
Do you want to take that one just for?
Sure, just to mix it up. So in general, El Nino leads to warmer temperature in global average temperatures than La Nina. So 2022 was a La Nina year. It was tied for the 5th warmest on record. It was the warmest La Nina year yet. We are now entering into El Nino, but it's still early. So the warming that we're seeing now is greenhouse gas driven predominantly.
Yeah, I mean, we're seeing the El Nino effects in the maps. If you bring up the map, you can see the band of red across the eastern tropical Pacific, and so that's adding to the temperatures. But the larger impacts of El Nino generally take a few months to manifest, and as El Nino builds, we expect that that's going to have more of an impact kind of early in 2024.
JS on YouTube asks, what about all these super strong storms around the globe? Will worldwide storms continue to get stronger?
So climate change does manifest itself in beyond just temperatures, and it does drive, for some impacts, increased frequency, for others increases in intensity, and for some types of impacts both. So for something like a hurricane, what we're seeing is more intense storms. So higher proportion of storms are categories 3 through 5. So we're getting a larger fraction of the hurricanes we do see are stronger. For heat, something like a heat wave, we're seeing more heat waves and more hot events. But each impact is a little bit different, both in where it occurs and also whether climate change is affecting the frequency, the intensity, or both.
We're also seeing more extreme wildfires, right? I mean, we have one burning in Maui right now. Can we talk about if we know whether or not climate change contributed to those fires?
Yeah, so wildfire is a complex phenomena. It depends on fuel, it depends on fire weather, it depends on ignition, and all of those things are kind of contingent on a lot of things that have happened over the last few decades. And so in Maui, you have the impacts of sugar plantations being abandoned, native grasses, non-native grasses coming in, a very wet spring that led to a lot of growth, and then a dry period more recently that led to a lot of fuel, and then you have the ignition and the driving factors of the fire from the tailwinds of Hurricane Dora, and so that's a pretty complex feature. But what we're seeing, if you look in general, is that we're seeing a tendency towards more and more intense wildfires, not just in Hawaii, but also in Canada and British Columbia and Alaska and the Rockies. And so these are factors where climate change is pushing the system, but there's lots of other things. In any individual fire, there'll be lots of other things that are antecedent to that.
Mm-hmm. And specifically to talk about the fires in Maui, there'll be a lot of research to look at that fire, right, to determine whether or not climate change affected that. Kate, did you want to comment on that?
Yeah, I think, as scientists and particularly the climate science community, whenever we see an event, we look into what is causing it, what do we know? We look at all the observations we have, whether they're from NASA, from others, and there are people that spend quite a bit of time looking at each of the different antecedents that Gavin mentioned and understanding those contributions, that we better understand both that event, but also that helps us better understand future events.
Gotcha. Kate, while I still have you, Goose Turtle on YouTube asks, how many satellites are in orbit monitoring climate change?
Oh, that's a great question. So NASA has more than 24 satellites and instruments in orbit, and including several on the International Space Station. So this is an animation of those right now, and we're continuing to add to that fleet. So we launched a set of 4 CubeSats recently that are looking at hurricanes. We also launched another satellite looking at air quality just this spring. But those are just the NASA satellites. So there are also other satellites monitoring the Earth and contributing to research on climate change from partners in other space agencies like European Space Agency, and a lot of that data is available and we can use it. There's also now commercial satellites that are helping contribute to monitoring of the Earth. And at NASA scientists have access to some of that information and can use that in their science.
Perfect. These questions are really great. We'd love for you to keep sending them in. Again, you want to use hashtag AskNASA on the social media platform or wherever you're watching us today. We'll be back with our guests to answer those questions. But first, have you wondered, is climate change the same as global warming? Let's ask NASA atmospheric scientist, Dr. Yolanda Shea.
Not quite. They each have their own meanings, but they are related. So what's global warming? We have seen an increase in the surface temperature averaged over the whole globe over the past century and a half. And that temperature continues to rise. NASA has analyzed data about the Earth's climate system from multiple sources that tell the same story. On a global scale, the Earth's surface is heating up because of the increasing amounts of heat-trapping greenhouse gases that have been released into the atmosphere from humans burning fossil fuels. That's global warming. Climate change is a more general term. It also refers to long-term changes over many decades or hundreds of years, but it includes all types of changes in the typical weather climate that can be and have been observed from regional to global scales. NASA has instruments that have observed a diverse collection of the current impacts of climate change, like decreases in ice in the Arctic, droughts, increasing wildfires, and increasing surface temperatures. These are all examples of indications of climate change. So is climate change the same as global warming? Not quite. They have their own specific meanings, but they are related to one another.
And one way we know they're related, right, is that greenhouse gases are causing both global warming and climate change. So, Gavin, as our entire Earth system changes, what can we expect in both the short and long term? You touched a little bit on this earlier.
Right. So right now we have a lot of factors that are kind of pushing us towards warmer temperatures. We got the El Nino. We perhaps have the volcano. There's some changes in marine aerosols. Those things are kind of adding to it. That will that won't all continue on at the same level, and so after the next couple of years we'll expect probably a slightly cooler year, but the long-term trends are going to keep on going until we stop emitting greenhouse gases, and particularly until we stop emitting carbon dioxide. At that point, the global warming at the surface will basically stop, which is great news. That means that we are in control of what's going to happen. Some of the other things, sea level rise, that's a lagging indicator, so that will continue to rise, though at a less accelerated pace. And so we can continue to expect those things. In a few years, we're going to have this same NASA Live thing, and we'll be telling you about how much warmer 2027 was than 2023. And I have been doing this for a while now. And I just want to make one thing very, very clear, that we take no joy in being able to predict these things. Normally scientists, we're supposed to be happy that we've understood something from the universe and that we've made predictions and our predictions come true. And we're supposed to say, yay, how clever are we? But these are predictions that we've been making since the 1980s. And as they've come true, and as we've seen, not quite the worst case scenarios, but pretty bad case scenarios eventuate, we're not happy. We would much rather have been wrong. And so as a scientist and also as a human being, these questions are troubling. I don't want to tell people what's going to happen, but I have to, right? Because this is what science is all about. But we take no joy in having our predictions come to fruition.
And when you're talking about this long-term trend, so is what you're saying, if we don't make changes now, these extreme temperatures that we're feeling now, years to come, could this feel cool to us if we don't stop what we're doing now?
Under almost all scenarios, these are the coolest summers of the 21st century.
Thank you, Gavin, for that. And for your explanation again about, not taking joy in this. We're here NASA is here to share the information so that hopefully it can drive change, right? So let's get to more of some of your great questions that you're asking online. Remember, keep sending them in using the hashtag AskNASA. Okay, so Mr. and Mrs. Smith on YouTube asks, have you seen a correlation yet between July's record temperature and the glacial melts? Kate, do you want to take that one?
So I think in general, what we see is that, with warming temperatures, we are seeing declines in glaciers and changes in the mass of ice sheets and that water, some of the Greenland and Antarctic ice sheet. We have satellites that have been measuring and monitoring that for more than 20 years. And so we can see those declines. We know that water is running into the ocean and contributing to sea level rise. So we know that general trend. I think, July just happened. So as scientists, we'll still look at exactly what the effect of 1 month is on that. But we know overall that climate change and increases in average temperature are affecting ice sheets, and that is affecting sea level rise.
Yeah, I mean, people are tracking glacial mass balance, so mountain glaciers particularly, and year on year on year, we're seeing losses to mountain glaciers, whether that's in Glacier National Park, in the Rockies, in the Andes, in the Himalayas. We're seeing decreases in that. You can go back to old photographs and compare them to what you can see now, and we're seeing retreat almost everywhere we look. So 1 month yes, that's going to add to the melt, but year on year on year, the overall warming is very clearly having a negative impact on mountain glaciers.
On Facebook, Sydney Alston asks, does the fact that the sun is in the solar maximum cycle have anything to do with the continuous record-breaking heat?
Great question, and no is the answer. So we're kind of moving into the solar maximum, and that would be expected to warm the planet a little bit. Roughly speaking, you get about 0.05 Celsius, maybe 0.08 Celsius from solar minimum to solar maximum, lagged by a few years because it takes a while for the oceans to catch up with the cycle. So there's a small lag. Where we are in the cycle right now, we're not really expecting anything other than a few hundredths of a degree Celsius. So it's kind of nudging us towards a warmer climate, in a cyclical way, but it isn't either driving the long-term trends or the scale of the anomaly that we're seeing this month.
Lots of great questions coming in on Facebook. This one's from Sofia Barriga. How much longer do we have to stop greenhouse gases being emitted by humans or to reduce pollution?
Yeah, I can take that one. I mean, I think the question is, how much warmer it gets depends on how much more we emit going forward. And so that, warming will stop when we reach what's called net zero carbon dioxide. So when the amount of carbon dioxide we're emitting is counterbalanced by anything that we're taking out, then you'll stop the warming from carbon dioxide. How much warmer we get at that point depends on how much more we emit until we get there. So there's, the amount of future emissions dictate the amount of future warming. We are, 2022 was about 1.1 degrees Celsius above the late 19th century average. And you've probably heard people talk about things like 1.5 degrees Celsius or 2 degrees Celsius as commonly discussed targets or goals. The expectations would be that, with continued emissions and current trends, we would be pushing towards 1.5 degrees in the near term.
Manav on YouTube asks, are we seeing a shift in seasons in terms of time of the year they happen?
Yes, we are. So in the Northern Hemisphere, we're seeing earlier springs, and we're not seeing the depths of winter that we were getting 100 years ago. And so that's shifting the timing of, leaf out, growing seasons, but also pests and insects and lake freeze and ice out. So it has kind of complicated effects on growing patterns. But yes, I mean, where we have the data to examine that, we are seeing shifts in the seasonal cycle as well.
Wow, so many different effects. And these questions are great. Again, just like really getting into how much we're being affected, right, by global warming and climate change. So again, thank you for all these questions. The next one is Colleen on YouTube, and she asks, what is creating the increase in methane in our atmosphere? Kate, if you want to take that, or?
I'll start. So, methane has a number of different sources. So some of the sources of methane are things like leaky oil and gas pipes. So as oil and gas will leak methane out into the atmosphere. All other sources include livestock, wetlands, rice, and the different sources around the world. This animation is showing atmospheric methane, and you can see the darker colors are where it's predominantly coming off of. But there are different sources in different parts of the world that are contributing to atmospheric methane.
Yeah, so atmospheric methane has more than doubled in concentration since the pre-industrial, and in the last decade has accelerated again. We're not really sure where that extra methane has come from. We think some of it is agricultural. We think some of it is a feedback, particularly from tropical wetlands. As they get warmer, they emit more methane into the atmosphere. So that's a feedback. It's an amplifying feedback on the system. And so, but we're still emitting a lot of methane from human activities. And one of the targets that people have looked looked at is whether we can reduce methane emissions, for instance, that have been leaks that have been identified from the EMIT satellite that was mentioned earlier on. Can we reduce the human contributions to methane to kind of bring that down? And I think that, personally, I think that that's a good target for us to be working towards. But there's a lot of very diverse sources, and so. But we do need to keep track of that. And one of the things that NASA is doing is trying to help people really see where that methane is coming from, so that we can get rid of the largest emitters.
Ahmed on X asks, how can individuals and organizations use NASA Earth data to make decisions about climate change mitigation and adaptation? We did talk a little bit about this before as well.
Yeah, I mean, I can start on this one. So we have a number of different tools for different applications. So I mentioned earlier that we have a tool called OpenET that's targeting farmers and how they can plan their irrigation. We have another application called Power that uses solar and meteorological data to help inform things like renewable energy. So understanding the conditions that it might be suitable for wind or solar power. We have other applications like Firms, which you might have seen in the news recently. It can show you where fires are burning. And so we make all of this data publicly available. We put it out in different places. We have different user communities that already use it. But one of the things we're working on now is trying to make everything easier to use and easier to find, so that people have the information that they need when they need it. And part of that is a part of a broader open science effort at NASA, where we're making not just the data available, but also tools and resources. We're also moving more data into the cloud so that you don't necessarily need access to a supercomputer to process the information we have. We're putting more trainings out, including translating some of those trainings into Spanish language. And we've also opened an Earth Information Center. There's a physical space in DC, but there's also a virtual presence. And the idea is to help find the information so people understand what data we have and how they can use it.
Yeah, let me throw in two more examples that we've worked with. One of the things that we've done is for the projections of climate change going forward, we've worked with NASA Ames to downscale that information to more local regions and produce diagnostics that are directly relevant to adaptation decisions. And we've worked with the NASA Sea Level Change team to produce projections at the coastal region that take into account land movement, that take into account regional sea level rise, so that you can have estimated changes to high tide levels in the 2040s and the 2050s that are important for planning decisions for infrastructure that's being built right now.
Yeah, I mean, knowledge is power, right? We should share, and then that's why we're doing what we're doing even today, right? Like answering people's questions so that, again, maybe it drives some of their decisions going forward. So I do want to touch on this again because we are getting a couple of questions about it still on social media. But Snoopy on YouTube asks, will it be getting hotter in 2024?
Unfortunately, yes. So as Kate mentioned, we're seeing the beginning of an El Nino. Generally speaking, El Ninos build towards the December, January period. And so we are expecting that that event will build over the next few months. And then there's a kind of a lag from what's happening directly in the Pacific to what's happening in the rest of the globe for various relatively complicated reasons. But the net effect is that when you start a year with an El Nino event, that year is generally above the trend line. And so we would be anticipating that 2024 would indeed be a record warm year, much like 2020, 2016, before that 2010, 2005, 1998. So this pattern has repeated itself multiple times. So we can say with quite some confidence that barring any other events such as a really big tropical volcanic eruption, we would anticipate that 2024 would be the warmest year on record as well.
Mm-hmm. I remember reading that these last 9 years, right, are the hottest collectively on record as well. Can you speak a little bit to that, Kate? Just again, to really show the trends we're seeing here.
Yeah, there's a long-term trend of increasing temperatures driven by greenhouse gases. We talked about that a little bit earlier, that things like carbon dioxide and methane, as they accumulate in the atmosphere, they're trapping heat. So the last 9 years have been the warmest since modern record keeping began, which means since about the late 1800s, which is when we've had these temperature records. And so we're seeing those increases in trends, and things like El Nino and La Nina may make an individual year warmer or hotter than that trend, but overall the trend is towards warming.
Yeah, I think I can predict what their headline is going to be at the end of the year, and it's going to be the last 10 years of the 10-year warmest years on record.
Yeah. All right, guys, keep sending in those questions again. Great. We love the interaction. We love that you're taking the time to chat with Kate and Gavin here. So please continue using the hashtag AskNASA, and we'll be back with our guests to answer some of those in just a few minutes. But first, if you live on the East Coast, you've probably noticed poor air quality during the past few months because of wildfires in Canada. In general, the air across the entire United States is cleaner than ever, but there's still a lot more we can be doing. Data from satellites, airplanes, and ground sensors, combined with data on race, ethnicity, poverty, and health, can unveil both the big picture of air pollution and individual neighborhood effects. Let's take a look at how this information is helping community leaders and other decision makers in Washington, D.C.
Take a deep breath. That very same air that's filling your lungs is full of millions of fine particles. Some so small that they can penetrate deep into your lungs and into your bloodstream. Right now, you are standing near the heart of Washington, D.C. Air pollution where you're standing has declined by 50% in the last 2 decades. And by no means is this by coincidence. Along with ground-based observations and field campaigns, NASA uses sensors aboard satellites and aircraft to obtain measurements of nitrogen dioxide, sulfur dioxide, and other pollutants near cities, suburbs, and major transportation systems. Because you can't fix what you can't measure. With the few ground-level air monitors we have in the city, it's very difficult for any individual to understand what pollution levels are in their neighborhood. NASA satellite data helps to fill in the gaps between those monitors so we can understand the different pollution levels experienced in different neighborhoods throughout the city. When coupled with socioeconomic data about race, ethnicity, poverty, and health, air quality observations help identify environmental challenges that disproportionately impact specific communities, and underline how much more work there is to be done to minimize pollutant exposure for vulnerable populations. Together, we can work to address long-standing inequities and ensure everyone has the right to a deep breath of fresh air.
So let's dig a little bit deeper here. Kate, how is NASA data helping to give us that fuller, more detailed picture of air quality across the US? And why is it so important, really, to even drill down to those neighborhood levels?
Yeah, thanks. And so as you saw in the video, some of the things we're doing is we're able to monitor air quality from space. So on the surface, we have these surface monitors, but they tend to be sparse. They're only where you put them. And one of the nice things about from space is we can see all of the Earth with many of our satellites. With others, we can see very high frequency measurements. And that gives us more information about what's happening. And that can be used to help people. So in addition to this, the information that was provided in that video, we've also just recently launched a new satellite called Tempo. It was launched in April, and it's going to provide hourly data over North America about air pollution. So it's just going to focus on North America, but it'll be able to provide hourly information. And one of the things that we'll be able to get from that is be able to see changes at like a neighborhood level scale at very fine time frequencies. So you'll be able to see things like rush hour traffic and the effects that it has on air pollution. We'll also be able to see things like wildfire smoke. So if you were in the northeast of the US in June and July, you experienced some smoke and air quality concerns from smoke that were coming from fires in Canada. Tempo will be able to give us that information. And with that hourly resolution over North America at a neighborhood level, we can use that to better provide air quality alerts. So people with asthma and respiratory illness will know when the air quality is poor outside and be able to take steps to protect themselves. You can also provide that information to decision makers to look at how to address air pollution in their neighborhoods.
I'm interested to hear, do you see big differences between neighborhoods in a different city?
You would see, because the sources of air pollution, so there are some sources that are more general and well spread, but other things like cars, so you will be able to see things along heavily trafficked, dense populated streets. Some other sorts of infrastructure will produce different types of emissions, so you will be able to see differences depending on where you look based on the activities on our surface.
Gotcha. Yeah, so again, that's why it's so important to get to that really granular level. All right, so let's get to more of your questions online. Keep sending them in using the hashtag AskNASA or put them in the chat where you're watching us. On Facebook, we have this question: with sea level rising, could this mean that certain areas of land will soon be covered by water in the future? And we also have a similar question from Pat on Facebook. He's asking, what inhabited areas will be most affected by the sea rise? He's heard that some of the island countries will be underwater.
Yeah, I can take
yes.
this. And so there's,
No. Go ahead.
Go ahead, Kate.
I'll start, Gavin, and then you can fill in. Yeah, so sea level rise, and there's global sea level rise that we can measure and monitor, but there's different regional sea level rise, and that has to do with things like gravity, the movement of the land, whether it's rising or falling. One of the things NASA's done is provide a tool, the NASA Sea Level Change tool, where you can look at different coastal communities, and you can see both how much sea level has risen in that area in the past. We also have an ability to look into the future. So you can see projections of sea level rise, and that'll give information to people about how much more they might experience for planning. And people have taken that kind of information and converted it into flood maps. So where might you see flooding? But there are different communities, based on the sea level that they're at right now, that even small amounts of sea level rise can have pretty devastating effects.
Yeah, I don't have anything. Go ahead. That's fine.
All right, Chris on X asks, when it's a cold winter, we hear the weather is different than the climate. When it's a hot summer, we hear this is a direct result of climate change. So which is it?
No, both. So if you look at the maps of any one month or any one year, you see structure, right? There are places that are a little bit colder, places that are a little bit warmer. But on average, what we're seeing is that there are many more places where it's warmer because of the underlying trends due to greenhouse gases than there are places that are cooler. So if you look at the map for July, there's a little slightly cooler patch in the Midwest and in Northern Europe. And some parts of Antarctica, but pretty much everywhere else is bright red, right? So the area that you're seeing, the increase in the amount of red on the map is a function of global warming, and so you still get weather, right? Weather hasn't gone away, but we're moving up, right? So the whole thing is kind of shifting towards those warmer temperatures. So there is a contribution to the July temperatures that will be just the weather, right? So there may be some aspects of, for instance, the North Atlantic temperatures that are contingent on just the pattern of weather that they've seen over the last year, but the overall trend and the overall impacts are indeed due to global warming and to the forced trend. So there's always going to be that noise on top of the trend, but the trend is very solid and is not going away anytime soon. So everything that you see is weather plus climate, and then the climate is pushing you towards warmer weather.
Thank you for that clarification. Several people on social media have asked about whether measurements or whether where our measurements are taken affects how accurate the measurements are. So specifically, they want to know if our measurements are being taken at airport tarmacs, making the measurements seem artificially high. Who wants to take that question? Sure.
I mean, so there's no there's no airport effect that makes temperatures warmer. That's just nonsense. We do use greenfield sites. There's been a lot of inner city sites that have been affected by urban heating. They've been moved mostly out of the cities so that we're not including the urban heating, which is a local effect, in those global averages. And then we can evaluate how well we're doing at getting rid of those local effects by looking at the satellite data, right? If you look at the maps of the satellite data, that has no issue with where the stations are. It's everywhere. You see the same patterns. And so what we're seeing, the records that we're seeing broken, the trends that we're seeing, they're not a function of issues with local temperature stations.
Right.
Just
You
to
guys
add
are
to what
looking-
Gavin said, and I think this is an important point that he's mentioning, is that we don't just use one way of observing or one way of understanding the Earth. Scientists are using multiple ways. So he's just talked about both surface stations and looking at satellite. They both show the same trends. We've also used models. He talked about reanalysis. That's using weather models to understand the past. And so we use all of those because we want to make sure that we really understand what's happening. And when we see the exact same effect in multiple ways, that gives us much more confidence in it.
Right, and there's different ways of processing this data. You know, you can say, okay, well, let me eliminate these dubious stations. Let me not make any corrections. But every time you do that, you basically just get the same answer. And so there's multiple products. You know, there's a product from Berkeley Earth that has a totally independent way of dealing with some of these non-climatic impacts in the weather stations. Comes up with exactly the same trends and anomalies. There's the Europeans, the UK Met Office has, again, an independent way of doing these things, and the correlations between these different time series are up at the 0.98, 0.99 level.
Some viewers want to know, how long does it take to gather all of this data for the temperature updates?
Yeah, so what we use, different national weather services produce different kinds of data that's used in different products. So they have daily data that they put out, the SYNOP data, which goes into the weather forecasts, and then at the end of every month they put out a monthly summary for each of their different stations. And so the data that NASA and NOAA are using is that monthly summary data, whereas the reanalysis and the weather forecasts use the daily data, and so they're a little bit different, and they have a little bit more information in the daily data, but we just use the monthly summaries, and so that takes a few days after the end of the month to come through. Generally speaking, we have a good estimate by the 8th of the month, and then there's usually a few late reports that come in, and so we wait about a week before we do the final test. But stuff will come in, over the next couple of weeks that refer to July, and so in a couple of months' time, when we redo it for August and September and December and the whole year, then things might shift a little bit as some of those stations report that have been a little bit delayed. But generally speaking, that's kind of well within our estimated uncertainty and doesn't really change very much.
This is an interesting question. Ira wants to know, are you using the info obtained from other planets' climates to influence decisions here on Earth?
So historically, the answer is yes. We had, for instance, measurements of aerosols in the clouds of Venus before we had measurements of aerosols on Earth. We knew more about the Martian ice cap than we knew about Antarctica because of instruments that NASA had sent to these other planets. With that information, and as we kind of had a pivot towards what was called Mission to Planet Earth in the 1980s, we kind of turned those instruments down to look at what the Earth was doing. And so a lot of the physics, a lot of the understanding came from the space program, came from planetary science. And now we're going back with the information that we've learned about how to model the Earth system. We are now applying that to the history of solar system planets through the history of the solar system, or to newly discovered exoplanets around different stars. What kind of climate are they going to have? How are they going to be? Are they going to be in the habitable zone for their particular star? And so we've seen, and I think this is one of the great things about NASA. We've seen this continuous interplay between planetary science, astronomy, earth science, the instrumental, the technology, and it all kind of comes together and plays off each other. So absolutely, we have used that information. We continue to use that information, and now we're kind of giving back so that we can have a better characterization of some of the wonderful new discoveries that we're doing in planetary science right now.
Kate, Daryl Murdoch on Facebook is asking, is our planet nearing the tipping point of no return? A similar question from Richie on YouTube. Is there hope of fixing this problem?
So tipping point has a very precise meaning in science, but what I think they're getting at is, will it be different, and I think there, what the future looks like depends on the actions that people around the world take. So future warming depends on future emissions. We know how to limit warming. We know that reaching net zero carbon dioxide will limit warming. We also have technologies available today that can reduce emissions. Some of those are developed by NASA in terms of aviation, some developed by other agencies or other countries. And we have that available, we have those options available now. And so we understand what's driving climate change. We understand what will influence in the future.
Perhaps the questioner is getting at the idea is, are things out of control? Are the feedbacks and the amplifying factors going to be so large that we can no longer control what's happening, and that it's out of our hands? And the answer is no. As best we can understand the situation, we are a long way from any kind of global tipping points that would make that true. And so what Kate says, let me emphasize that. What is going to happen depends on what we do. And so we have agency. In other words, what we do as a society is going to control what the temperatures are going to do, what the sea level is going to do, and how those impacts are going to affect us. So it isn't. We have not passed that tipping point, if you like.
So we're running out of time. We only have 30 seconds left, but I do have this final question. How can NASA meet the scale of this challenge now that we've been talking about some serious challenges we have ahead with climate change? How can NASA meet the scale of this challenge, not only now, but in the future? And we'll start with Kate to give an answer for that.
Yeah, I think a lot of the work we're doing to observe the planet, to understand the drivers, to project into the future and provide that information, continuing to do that, to expand that information so that we have more and we can provide it to people so that people understand what's happening in their communities and can better plan for their future.
Let me be totally honest. It is a real challenge to scale the information that we have available to all the different decisions and stakeholders that exist, not just in the US, but around the world. It's a massive challenge. And, we are looking to anything that will help us do that. We're looking towards artificial intelligence and machine learning. We're looking towards cloud computing. We're looking towards distributed systems. We're looking towards better visualizations. We're trying everything that we can to make that happen. And we aren't quite there yet. I think Kate would probably agree with this. We have some ways to go, but it is definitely the direction in which we are wanting to go. And anybody that has ideas or facilities or ways in which they can help that effort, we are absolutely willing to listen to that and work with folks all across the spectrum.
Dr. Calvin, Dr. Smith, thank you so much for chatting with me and everyone who sent in questions today. It was really helpful. And again, when we are thinking about the future, it really starts with having this conversation, discussing what the science is showing us, and moving forward in a thoughtful way. So thank you both.
Thank you.
Thank you.
All right, and thank you again to everyone who joined us online. I love that we were able to answer really so many questions from all of you, and they were really great questions. So again, thank you so much, and we hope you'll continue following NASA's efforts to study and protect our home planet. To stay updated, follow NASA Earth on Facebook, X, and Instagram. And remember, from space, sky, sea, and land, NASA provides detailed climate data and research to the world. All of this data is freely available to anyone, and you can access that information and more at climate.nasa.gov. Thank you, and we'll see you next time.